Now let's continue with topology of transportation networks. Topology, this word itself, it refers to a branch of mathematics concerned mainly with properties of a geometric object. And this geometric object is usually a network. Since we're trying to address transportation networks, so naturally topology can be a concept applied to transportation networks, right? So here are some examples of topologies, different types of topologies for transportation network or for other networks. So here we only have nodes, we have links, but these networks, they are not necessarily transportation networks. Okay, so four types of them, very typical example. Let's just simply go through them. So mesh network, okay, or mesh topology, at least two nodes with two or more links between nodes. Okay, and for hub and spoke structure or topology, um, peripheral nodes are connected to a central node, which is the hub. So we have 1, 2, 3, 4, 5, 6, 6 peripheral nodes and a central node, right? And we also have very simple, straightforward linear topology, only one link between each node pairs, and where each node has a maximum of two links. Okay, each node can only be connected to other two nodes, which means two links, right? And we also have this tree structure. It's just like the tree data structure from computer science. So all nodes converging to one node from a hierarchy of other nodes. So here, the most important node here is considered as the root of the tree. And this tree has branches, right? And eventually we have leaf nodes, right? This 1, 2, 3, 4, four nodes. At the ends of all those branches, they are considered leaves, okay? And now let's talk about the calculation of number of links, just very simple discussion here. So geometry and number of links needed for given nodes, okay? So if we want to create something called minimally connected network, for all the nodes to be linked together, that's the only requirement, okay? It is also called as minimum network. So how many links do we need for this minimum network? The number is calculated as n minus 1, and n here represents the number of nodes. So here we have 1, 2, 3, 4, 5, 6. 6 nodes, 6 minus 1 equals 5, right? Very simple. So we have another type of network is called fully connected network or complete network, for each node to be linked to all other nodes. Okay, so this is a fully connected network or complete network. So in this network, each node is connected to all other nodes, which means that you have to exhaust all possibilities for each node, right? So each node needs to be connected to all rest nodes. And the formula here for the number of links is still very straightforward. N multiply n minus 1, then divide that value by 2. So here we have 1, 2, 3, 4, 5. 5 nodes, n equals 5. So 5 multiply 4, which is n minus 1, right, equals 20. 20 divided by 2 is 10. Okay, and the third network I want to discuss here is a little bit special. Okay, so for each node to be linked to all other nodes, this part, it is the same as complete network, right? But the second part of the requirement is special, but there should not be any intersections of links. So for complete network, we can say there are multi-intersections among links, right? Which means that they can intersect with each other. But here you can say for this network, we have two very strange links here, right? They are not linear, but they're still connecting two nodes. Okay, and this type of network is called fully connected planar network. Okay, for this type of network, the number of links equals 3 multiply the difference between n and 2. So here we have 1, 2, 3, 4, 5, still 5 nodes, just like this complete network, right? Still 5 nodes. But the number of links here is only 3 multiply the difference between 5 and 2, which is also 3. So 3 multiplied 3 equals 9. Okay, one less link compared to fully connected network. Okay, because you said that there should not be any intersections of links. Okay, so some examples here. So how many links are needed for a minimally connected network? The answer is n-1. You can use it to verify if you have created a correct network given the requirement here. For example, we have two scenarios here. I'm going to exit presentation and show you how to draw transportation networks. Okay, let's just insert a straight line, make it green and thicker. How to do that? Let me say, wait, yeah. Okay, so on the left side, we have 1, 2, 3, 4, 5, 6, 7. 7 nodes. According to the formula, when we create a minimally connected network, there should be 6 minus 1 equals 5 links, right? Let me try. So link 1. Link 2. Link 3. Oh, sorry, we have 7 nodes here, right? So 1, 2, 3, 4, 5, 6, 7. 7 minus 1 should be 6, right? So now I've just finished creating this transportation network with 1, 2, 3, 4, 5, 6, 6 links, right? N minus 1 equals 7 minus 1 equals 6. So on the right side, similarly, you can use this green lines to create a very straightforward, minimally connected network. And you can see that there are multiple answers here for the network. What I'm trying to draw here is just one of them. Oops, 1 second. So yeah, connect them like this. One more. Right? So this is an example. So we have, for this specific scenario, obviously we have 9 nodes. And if the network is minimum network, there should be 8 links, right? 9 minus 1 equals 8. So 1, 2, 3, 4, 5, 6, 7, 8. Like I said, this is only one possible answer. If you do this, right? You move this to the top, move this link to the bottom. This is another answer, another solution, but still 8 links, right? So let's do more. How many links are needed for fully connected network? N multiply n minus 1 divided by 2. So for the left side, 1, 2, 3, 4, 5. 5 multiply 4 divided by 2. So we should have 10 links, right? Let me just use the segment I used before. This is more complex, so it takes more time. And there could be mistakes, so bear with me. So let me try to just connect each node to rest nodes. Okay. So let me just create a loop first. Okay, so now we have 1, 2, 3, 4, 5, 5 links, and connect each node to all rest nodes, which means this, right? So let's continue. This one to this one, also this one to this one. Okay, let's count the number of links. 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. Where is it? Let me say, yeah, here we go. We have another one here because these two nodes, they're not connected. Now we have 10 links. We have 10 links. So 5 nodes, 5 multiply 4, 20. 20 divided by 2, 10. Yeah, here is the solution. But you should know that for fully connected network, the solution is exclusive, which means this is the only solution. It's not like the minimum network, okay? Because you have to fully connect each node, so there is only one solution. So on the right side, we have a even more complex scenario. So 1, 2, 3, 4, 5, 6. 6 multiply 5, which is 30. 30 divided by 2, 15. So 15 nodes. So 15 links. So link 1, link 2. Link 3. Link 4. Yeah. Link 5. Okay, let's continue. There is a central node here, link 6. Link 7. Link 8. Link 9. And link 10. Okay, where are the rest 5? So this link, this node should be connected to this node, right? So link 11, link 12, link 14. Where is the last one? This node needs to be connected to this node. Okay, now we have 15 links. So 6 nodes, 6 multiply 5, 30 divided by 2, 15. Okay, so here when you're trying to establish a network like this, you need to be very careful. You need to make sure that you have exhausted all the links, all the connections, because each node needs to be connected to all rest nodes. Okay, so next example here, let's talk about how many links are needed for fully connected planar network. There should be no intersection of links. Okay, the number should be n minus 2 multiplied by 3. So now we have 1, 2, 3, 4, 5, 6. So 6 minus 2 is what? 4. 3 by 4 is 12. Right? Okay, let's get started. So link 1, right? Link 2, link 3, link 4, link 5. Okay, the principle here is very similar to fully connected network. Each node has to be connected to other nodes. So the central node here also needs to be connected to the rest nodes. Okay, so now we have 5 more links for the central node here. Okay, now we have 10 links. So the result should be 12, right? Where are the rest 2? And the rest 2 should not have intersections with the current 10. Okay, the rest 2 is a little bit complex. Let me use this. Right, 11, link 11, and link 12. Where is it? Link 12. Okay, you cannot if I have finished drawing these 2 spatial links, there is no other possibilities to draw other links connecting 2 nodes without any intersections with the current links. If you do not believe, you can try. Okay, it's not possible. And here, for the main frame or the first 10 links of this transportation network, positions of them are fixed, right? For all those green links, the positions of them have been settled. There is no other probabilities or possibilities for the change of them. But for the last 2 links, they are spatial. Now I'm using this this blue link to connect this node and this node, and also this node and this node. But is there any other possible solutions? Of course. Let me just delete them. This time I'm not connecting the original 3 nodes I just did. How about this? Right? And after that, let me just connect this node with this node. Right? Still, there is no intersection, and there are 12 links. Okay, so for a fully connected planar network, there could be multiple solutions. Okay, how about the right side nodes here? So 1, 2, 3, 4, 5, 6, 7. 7 minus 2 equals what? 5. 5 by 3, 15. Let me find out all those 15 nodes, links. 15 links. Link 1, link 2, link 3, link 4, link 5, link 6. Okay, if you compare the left nodes and right nodes, although on the right side we have more nodes, but the structure, the spatial distribution of them stays the same. Several surrounding nodes and one central node. So even there are more links, it's easy to exhaust all of them, right? The structure here stays the same. Just use the principle here, right? Connect each pair of nodes, right? Start from surrounding nodes and then take care of the central node. Okay, here we go. Now we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Well, 12 links, right? So now we need to think about the rest several should be 3, right? 3 links that do not intersect with the rest links. Link 1, link 2, and link 3. Here we go. Right. Again, Again, there are other solutions, right? If you do not connect these 2 links, instead of that, you connect these 2 nodes, with a link. Then the rest 3 links will change. And what I'm showing here is just one of several solutions here. Okay, so here we discussed a little bit about calculations for number of links needed for each type of network: minimum connected network, a fully connected network, and also a fully connected planar network. Okay, I would suggest devising some questions, devising some scenarios for yourself, and try to connect these nodes and using different requirements for different types of network, and say if you have done correct work. There might be questions in your exams regarding establishing different types of transportation network. So yeah, just use paper and pen. It's more convenient than slides to do some practice. I'm doing this on slides because I need to show you the process, right? Okay, let's continue. Let me get back to the presentation. And so we have fully connected network. We have minimum network, right? And we have some networks between these 2 types of networks, right? And we're just putting this different types of network within this 2-dimensional space with coordinates, right? Horizontal axis is for network length. Okay, the total network length. And the vertical one is for average path length. Okay, and for type A, which is minimum network, it is the simplest topology, weakest connectivity. Because if you want to start from one node and get to another node, there is only one solution for you, one path for you. Okay, so path length means that the distance you travel from starting point to destination. The network length means the total length of all links within a network. So it's different, right? Right. So when the network is very easy, straightforward, the network length is minimum, right? Because you use the least number of links to connect all nodes. So the total network length is minimum, But when you consider traveling from one node to another, because you only have one option, and that option most likely is not the minimum possible distance between two nodes. So your average path length or travel length is very high, right? Because for example, if you want to travel from this node to this node, obviously the shortest distance exists along the straight line between these two nodes. But since this is a minimum network, this shortest node link is actually not there. You have to travel from this node to a second node to a third node to the fourth node to the fifth node to get to the destination. So the average path length or travel length is very long. Okay, that's minimum network. On the other hand, another extreme here, graph D, or say network D, a complete network, which means that each node is connected to all rest nodes. So complex topology, the structure is very complex. The network length is maximum, which means that you need a lot of money to create a network like this. But it has the strongest connectivity with huge redundancy. Okay, it means that if you want to start from this node to this node, there is a straight line, a straight link connecting them. Actually, there is a link. Okay, I mean, connecting each pair of what? Nodes, right? And here, I think I just found a mistake here. This node and this node, they are not directly connected, right? I think that's for the convenience of graph making, because if you connect this node and this node, there should be a gray line very close to this middle node, which can be very confusing. But I would say that this graph D is not correct for a complete network. Let's just consider it as a correct complete network, okay? But yeah, like I said, for this network, there are just so many links. You have to construct all of them. But it's very convenient, right? If you want to travel from node A to node B, I mean, there is a direct link between any pair of nodes. So the average path length or travel length is very low. But like I said, A and B, they are extreme examples. B and C, intermediate networks. Okay, somewhere between minimum network and complete network. They are usually what we say in real life. There is always compromise between simplicity and connectivity. Compromise is actually a good thing, according to my experience, for most scenarios. Okay, usually you do not want to pursue a very extreme scenario. Okay. Okay. Now let's talk a little bit about physical grounding. Territorial occupation of transportation networks, because the networks we talked so far, they are abstract networks. We do not consider if they have occupied real world space. Now let's talk a little bit about that. So there are clearly defined transportation networks. Okay, they have specifically, they have clearly defined territorial occupation in real world, okay, with a well-established land ownership along their path, for example, highway or railway. This implies only one exclusive use and other functions are not possible. Railroad is only for trains to go through, right? Highways, they are only for cars and trucks. They are not for trains. Railways, they are not for cars and trucks. And neither of them is for pedestrians. So that space occupied by railways or by highways, that space is exclusive for them, okay? It's only for them. And we have a vaguely defined territorial occupation, okay? Most maritime and air corridors are vaguely defined as multiple use of space is permitted. For example, there is maritime corridor between, say, China and Japan. But does that mean this corridor exclusive to cargo ships? For cruise? No. If you are a fisherman, you can use your boat to fish within this corridor. This corridor is more like a more abstract concept. The corridor is not right there compared to highways. When we are thinking about highways, there are road shoulders, there are bridges, right? These bridges, these road shoulders, road boundaries, they strictly defined the space occupied by highways. But is there walls or shoulders or any physical boundaries for maritime corridor? No. Similarly for air corridor, right? Planes can just fly from one city to another to form a trajectory, and air corridor, and this trajectory should be within a specific air corridor, right? But does that mean the space used by this airplane can only be used by airplanes? No, a bird can still fly within that space, right? Although it's dangerous to planes, but it's not exclusive to anything, right? So, but still there is trajectory for cargo ships, for airplanes, for birds, for fishermen, but for fishing boats, and there is vaguely defined boundaries. Okay, but the third type here is without definition, right? For example, we can consider telecommunication networks as transportation networks. Transportation of what? Electromagnetic signals, right? Right. So if we look at telecommunication networks from this perspective, right? Each signal, each group of data traveling within this network is something like a vehicle, like a person, like a cargo. Then telecommunication network is actually transportation network, right? And here we have territorial occupation without definition. So in many telecommunication networks, overlapping is frequent, and there is also no service zones, right? So you can see here, talking about boundaries, yes, there might be vaguely defined boundaries for each node here, and each node can be considered as a signal tower, or we call it base station for telecommunication networks. Each one is serving a specific area, so you can consider there are boundaries, but these zones covered by different base stations, they overlap each other, which means that multiple areas, multiple telecommunication regions, they share the same space sometimes, right? So there is no definition of territorial occupation, right? Okay. Three types of physical grounding of transportation systems. Okay, that's all you need to know. Okay, for this class, you do not have to dig even deeper. Okay, then I want to talk a little bit about continuity of transportation networks. I did not list continuity at the very beginning of this lecture as an aspect of transportation networks because I personally think that continuity is a part of topology. Why? I will show you examples. So transportation networks are to link locations and thus confer a level of spatial continuity. What does it mean? So for example, we have graph A with two small transportation networks. The one on the left side looks good, right? Within this network, continuity is good. We can say it's not fully connected network because you can find a lot of pairs of nodes not connected. On the right side, we have another transportation network. It's simple, but the continuity within is good. And we have graph B with another transportation network with low level of continuity. Okay, not all nodes are connected here, neither here or neither here. So I would say continuity is good or is okay within each network, but the level is not high. How to achieve the best continuity for a specific network? Make it a complete network. Okay, now let's continue. So we have two small networks in graph A and another one for graph B. What if we combine them? Use the third network, which is the yellow one, to connect two networks. So originally, these three networks, they're okay about their continuity within, but they are separated from each other, especially the two networks in graph A. But now we use the network from graph B to connect two networks from graph A. So now we have a high level continuity transportation network. Again, it's still not fully connected, all those nodes in this network from graph C, because it's not a complete network. But compared to three small networks from graph A and B, the continuity here is much higher. Okay, so this is called continuity. And we have several shared nodes, right? 1, 2, 3, 4, 5. 5 shared nodes. Okay, why are they called shared nodes? Because these 5 nodes, they are shared by 3 small networks. If we consider this huge network is made from 3 small networks, right? If at the very beginning you consider this whole network is simply one network, then there is no so-called concept of shared nodes, right? Because they're shared by 3 small networks. So these shared nodes could be intermodal nodes or transmodal nodes. These two concepts, they are the last part of this video, okay? So what is intermodal? What is transmodal? So intermodalism, if the transportation network is following intermodalism, then there should be multiple modes found in this network. For example, we have road and rail. They both belong to land transportation mode. And we can still find the second mode here, maritime. Right? So from origin to destination, we used 3 types of transportation, road, rail, and maritime, but 2 modes, land transportation, and maritime transportation. Okay, and there could be multiple contracts, right? If you want to move something from city A to city B, there could be multiple terminals between these 2 cities. You may need several tickets or contracts to finish this movement of goods or cargo. okay? And we also have a gateway node here. What is a gateway node? It is a node in which you can change the mode of transportation, right? At this specific node, land transportation was abandoned, and you choose to use maritime transportation to finish the last segment of the journey of this cargo or this good or this person, right? And we also have transmodalism. In this type of transportation network, there are multiple nodes, of course, origin, destination, and maybe another node or for you to rest or to just use another contract maybe, but there is only one transportation mode, which is what? Which is land transportation, railway. And between intermodalism and transmodalism, we have multimodalism. Multimodalism is actually a type of intermodalism. The only difference is that you use one single contract, okay, to finish the whole journey of this cargo from origin to destination using multiple modes and types of transportation, right? So 3 types of transportation, right? Road, rail, and maritime. And 2 modes, land transportation and maritime transportation. Okay, okay. That's all I want to talk about. The different aspects of transportation networks. Okay, and then for next week, for the whole week, we're going to talk about the evaluation, quantitative evaluation of transportation, of the risks of transportation networks. Okay, there will be some calculation, of course, some graph rating, and you need more practice on that topic next week. So that's the reason why I will only provide the content for transportation risks next week, okay? And you can consider that as one lecture, and for the rest time of the week, which should be another lecture, you should practice, okay, and prepare for the exam, because evaluating the risk of transportation system will be a part of the first exam. Okay, too much information for this video. I will stop here. Thank you.